Hello, I'm Yashvi and Adisha work on the deep learning project, which is deep learning for anomaly detection in time series data. In this video, we are going to learn how we did this project and what do we infer from this project. So we'll explore the potential of deep learning models like stacked autoencoders and convolutional neural networks to detect anomalies in time series data. So let's get started. This will be the table of contents. We'll start with introduction and background. Then we'll understand industrial applications and the challenges that we face in classical approaches. And then we'll go into our model, which is deep learning for anomaly detection. At the end, we'll do some comparisons, which is comparative reviews, and we'll end with conclusions and guidelines for new practitioners. So let's get started with introduction. We'll first understand the importance of data. So data collection and analysis have become crucial in industries such as business, finance, healthcare, and manufacturing. Challenges that we face in data analysis are as the volume of data increases, it is difficult to find an effective analysis technique to extract meaningful insights from the data. And anomaly detection is a critical task in data analysis. Anomalies can indicate potential risk, inefficiencies, and security threats. What is anomaly detection? Anomaly detection refers to the process of identifying patterns or instances that significantly deviate from the expected behavior in dataset. Anomalies can be outliers, rare events, or abnormalities. Anomaly detection plays a crucial role in ensuring system integrity and security and reliability. And what is time series data? Time series data is a collection of observations recorded over time, where the order of observations is significant. It is encountered in various domains such as finance, weather forecasting, and sensor data. What is importance of anomaly detection in time series data? Anomaly detection in time series data is particularly challenging due to the consideration of temporal dependencies and relationship between variables. Detecting anomalies in time series data can prevent accidents, economic losses, and improve system performance. Deep learning based methods have shown promises in addressing these challenges. We'll start with what is background. Here we'll discuss about elementary background on anomaly detection in time series data. So there are various types of anomalies that exist in a time series data. Basically, we are going to discuss about the four basic anomalies: point anomaly, contextual anomaly, collective anomaly, and other anomalies. So what is point anomaly? Point anomalies refers to data points or sequences that abruptly deviate from the norm. Causes for this type of anomalies can be that they may appear as temporal noise and are often caused by sensor errors or abnormal system operations. Detection can be done through detection point anomalies involve setting upper and lower control limits based on prior data and identifying values that exist outside those limits. Now we learn about contextual anomalies. So contextual anomalies represent data points or sequences that when considered within a given context deviate from the expected pattern or shape. These anomalies can be challenging to detect as they do not necessarily fall outside predefined limits but exhibit unexpected behavior within a specific context. Detecting conceptual anomalies require identifying unexpected patterns or shapes within a specific context. So collective anomalies refers to a set of data points that gradually show a different pattern from normal data points. And causes can be individually these data points may not appear anomalous, but collectively they raise suspicions. Detecting collective anomalies require considering long-term context and identifying patterns that deviate from the expected behavior. Although anomalies can be identified as other anomalies, these anomalies may exhibit unique characteristics or patterns that deviate significantly from the expected behavior. Detecting and understanding these anomalies require domain-specific knowledge and tailored anomaly detection techniques. So properties, time series data are temporality, dimensionality, then non-stationarity, and noise. So temporality is time series data is a collection of observations indexed in a time order. Each data point depends on its past values. The temporal correlation or dependence between consecutive observations is a fundamental characteristics of time series data. Understanding the temporal nature of data is crucial for detecting anomalies and capturing patterns over time. Dimensionality: time series data can be univariate or multivariate. Univariate time series data consists of single variable. Multivariate time series involves multiple variables that may exhibit correlations and dependencies. Analyzing multivariate time series requires considering both temporal dependence and correlation between observations. Now learn about non-stationarity. Stationarity refers to the statistical properties of time series remaining constant over time. Non-stationarity occurs when the statistical properties of data change over time, such as mean, variance, or distribution. Non-stationarity poses challenges for anomaly detection as the expected behavior may vary over time. So, noise. Time series data often contains noise, which refers to random fluctuations or errors in the data. Noise can obscure pattern and make it challenging to detect anomalies accurately. Pre-processing techniques such as noise reduction or smoothing may be applied to improve anomaly detection performance. Now learn about the industrial applications for this model. There are basically four industrial applications that we are going to discuss: smart manufacturing, smart energy management, cloud computing systems, and structural health environment. Let's start with smart manufacturing. In smart manufacturing, we can use anomaly detection in various domains, such as production equipments. Production equipments in smart factory refers to the machinery and systems used for manufacturing product efficiently while maintaining the quality. So anomaly detection is a production equipment in production equipment is crucial for identifying possible failures and abnormalities without extensive domain knowledge. Deep learning models such as autoencoders based on long short-term memory have been used to learn the normal state of equipment and detect anomalies in multivariate streams occurring in production equipment components. Next domain that we can use is infrastructure facilities. Infrastructure facilities such as pumps, chillers, and scrubbers play a vital role in maintaining environmental conditions in industrial settings. Anomaly detection in infrastructure facilities is important for enhancing the stability of manufacturing process and predicting failures. Deep learning techniques, including discrete wavelet transform (DWT) and LSTM-based autoencoders, have been applied to detect anomalies across multiple pumps and recognize failures in infrastructure facilities. Also, we can use this for logistic automation systems. Logistic automation systems such as autonomous guided vehicles are used in manufacturing industries to transport products components between work areas. Anomaly detection in logistic automation systems help ensure smooth operations, reduce cost, and enable on-demand changes in product types. Neural network-based methods and decision trees have been employed to monitor the condition of AGVs and detect unplanned stopping or slowing of vehicles in factories. Now we'll discuss about how we can use anomaly detection in smart energy management. Smart energy management systems aim to achieve stable energy supply and efficient consumption to address climate changes and resource constraints. Under smart energy management, we'll discuss how to use anomaly detection in electric powers. Anomaly detection in electric power systems involve monitoring power plants and consumer side losses. Deep neural network models such as convolutional LSTM, CNN, and attention layers have been used to detect anomalies in multivariate time series data generated by power plants. These models are not only models not only identify anomalies but also diagnose the severity of problems, helping in maintaining stable power supply and preventing losses. You can also use this for treated water and manufactured gas. Water treatment distribution systems play a crucial role in ensuring the quality of potable and industrial water supply. Anomaly detection in treated water systems involve monitoring distribution networks of physical attacks and cyber intrusions. Real-world datasets such as SWOT and WADI have been released for researchers to develop anomaly detection methods in water systems. Manufactured gas in the purification and refinement process in manufacturing petroleum products directly impacts their quality. So anomaly detection in manufactured gas systems involve monitoring the purification and refinement processes to ensure quality and safety. CNN-based have been proposed to detect anomalies such as gas leaks by monitoring flow noise inside the pipes. You can also use this technique in cloud computing systems. Cloud computing systems involve the storage and management of client data in remote data centers by service providers. Server machine. Anomaly detection in server machines involve monitoring multivariate time series metrics such as processor load, network usage, and memory status. Variational autoencoder and gated recurrent units has been proposed for monitoring server machines and detecting anomalies. The combination of VAE and GRE allows for the extraction of hidden states and reconstruction of input data, enabling effective anomaly detection. Network and framework. Monitoring network systems and distributed processing frameworks is crucial as network traffic grows exponentially. Anomaly detection methods such as adversarial autoencoders and graph attention networks have been proposed to identify anomalies in network systems and big data processing frameworks. These methods leverage techniques like attention layer, recurrent units, and forecasting to capture temporal dependencies and improve anomaly detection performance. Cybersecurity cloud computing systems face the threat of malicious cyber attacks, making cybersecurity a critical aspect. Various methods have been proposed to protect customers' sensitive information and ensure the security of cloud systems. These methods employ techniques such as encryption, access control mechanism, and data anonymization to safeguard data in cloud environments. Now learn how can we use anomaly detection in structural health monitoring. Let's start with the definition. SHM evaluates the load and responses of civil infrastructure. It identifies abnormal behaviors to ensure structural integrity. Our objective is to detect damages, corrosion, or anomalies to prevent failure, enhance safety, and prevent accidents in structure. Data collection involves various measurements collected from sensors installed in various structures, and data analysis is done by identifying deviations from normal patterns, detect potential structure issues. Challenges that we face during this is eliminating anomalies from the imperfect sensors or data transmission, ensuring reliable monitor results. The method that we use is utilizing various techniques, analyzing data, identifying abnormal patterns, and predicting remaining useful life. Importance is to maintaining safety and reliability of civil infrastructure and continuously monitoring for early anomaly detection.